Okay. Firstly, thank you to Laura, Liam, Maria, and Oliver for giving me this opportunity to present this work, and perhaps an even bigger thank you for keeping this thing alive and kicking for the last. This is the 5th iteration, so kudos on that as well. So I'm going to talk about some work joined with my fantastic collaborators, Philippe Nadeau and Hunter Spink. So this title is Quasisymmetric Divided Differences. So let me get right in. Okay, so that's the aim. The aim is to build a theory parallel to the extremely rich theory of Schubert polynomials, rich both from the combinatorial perspective as well as the algebro-geometric perspective. And the genesis, the origin of this classical theory is in these operations on polynomials called divided differences. Okay, and somehow the theory of Schubert polynomials is tied in with symmetric polynomials, informally because Schubert polynomials are generalizations of Schur polynomials. And so one could inquire, well, is there a parallel story which involves quasi-symmetric polynomials? And my intention is to convince you that the answer is yes. So here's a vague outline, some classical stuff to begin with, and then I'll talk about these two topics, bullet point 2 and 3. So this is stuff we just put out at the beginning of this month, and finally I sort of want to present some applications to known things. So I'll revisit Schubert expansions. The proof of the pudding is in the eating, so I'll give something back to known results. Okay. All right. Okay. So let's quickly recall what it means to be symmetric. If you hand me a polynomial in n variables, I can move the variables around. So I can pick a permutation. I can reindex the variables according to this permutation. And if I get the same polynomial back, regardless of the rearrangement I do, my polynomial is symmetric, right? So let me just record that as invariance under permuting variables. Okay, so this quasi-symmetric definition is way more verbose than the one that I just presented. So let me just read it out loud and then extract what I consider to be the essence of this definition. So you start with, you hand me any list of positive integers. I look for the coefficient of the monomial x1 to the a1 through xk to the ak. And the same coefficient should appear with any monomial of the form x sub i1 to the a1 through x sub ik to the ak, where the ij's are strictly increasing. Okay, so the way you should think of this is you have some monomial that's left justified, so x1 to the a1 through xk to the ak, and you insert some space between these indices, so you spread the monomial out, and this is sort of one of the ideas underlying Pechenik-Satriano's work on James spaces as well. So let me record this as invariance under shifts. Okay. So symmetric polynomials invariant under variable permutation, and quasi-symmetric polynomials invariant under shifts. Okay, so knowing well that understanding the action of the symmetric group amounts to understanding what's happening with simple transpositions, we can just focus on the case of two variables, because I think this is instructive. So a polynomial is symmetric in two variables if you can swap and take differences, and you get 0, right? So on some level, though, this is mildly unsatisfactory, because if you notice this expression, it's divisible by x minus y. Okay, so there's some redundant information here. So you divide by what's redundant, and then you get something that knows the core. So this is the divided difference operation. It maps polynomials in two variables to polynomials in two variables. Okay, so this is a very well-studied BGG operator, or goes by several other names due to BGG and Demazur in the 70s. And I sort of want to mimic this story with quasi-symmetrics. And you realize that it looks sort of dumber, right? A polynomial in two variables is quasi-symmetric if this equality happens. So you shove in 0 in the second coordinate, and then you swap, and then you get 0 again. Okay, so this difference captures quasisymmetry. And again, you should notice that plugging in x equals 0 gives you identically 0. So there's redundant information. So you should divide out by what's redundant. So this operator T is now a map from the polynomial ring in 2 variables to the polynomial ring in 1 variable less. Okay, so it's different from divided differences here already. When you shift things that are already on the edge, they get lost, right? They drop off. So the number of variables shrinks by 1 when you shift. Okay, so I want to call this the Quasisymmetric divided difference operator, but I should have good reason. So let me tell you some things that hold in the case of Schubert polynomials, and then see if I can come up with the parallel story. Okay. Any questions at this stage? So I'll trust that someone will interrupt me if there's anything in the chat that needs addressing.
Can you say maybe again why one of the variables falls off the end? I think I missed.
So if you think of quasisymmetric functions, there's infinitely many variables, so you don't see this issue. But if you work with a finite set of variables, right, the shift invariance, if xn was being used and you shift something, the xn sort of goes away, right? So working in this finite setting is what's causing this oddity.
Okay, thanks.
Yeah. All right. Okay. So let me keep going. So let me give us some ideals to emulate by reminding you of 3 things maybe that hold in the classical story. So now I'm going to work with the polynomial ring in infinitely many variables. My divided differences are going to act on consecutive variables x sub I and x sub I plus 1. Here's a list of facts in sort of increasing order of difficulty maybe. The joint kernel of the partials are simply the symmetric polynomials, right? Easy to verify. The full list of relations between these partials are these nil-Coxeter relations. Observe the braid relation, as well as this commutation relation. And this sort of tells you that composing these divided differences translates it into the combinatorics of reduced words. Okay, so composites of divided differences are indexed by permutations. Okay. And from there on, you have this fantastic basis of polynomials, which many in the audience will have studied and contributed to as well. I'm going to use the very bare bones definition, so no combinatorics. The Schubert polynomials are characterized as the unique family of homogeneous polynomials such that the Schubert index by the identity is 1. The degree of a Schubert is the length of the indexing permutation. And this sort of magical event, when you act on a Schubert with a divided difference, you either get 0 or you get another Schubert of degree 1 less. Okay, and the indexing permutation of that Schubert is W times S sub I, where S sub I is a simple transposition, swapping I and I plus 1. Okay, and just to be complete, des W is the set of descents of a permutation. So it's indices where you drop down when you read things in 1-line notation. Okay, so I sort of want to use this as the compass to guide what's coming next. Right, so just a figure to go along, that characterization does not immediately imply that these Schuberts have non-negative coefficients in the monomial expansion. Okay? But they do. So here's this little bit of a graph that shows how you act on Schuberts, applying dels, and you eventually become 1. Okay, okay, so here's the overarching question that what can one say about these quasisymmetric dels that I introduced earlier, right? So what's the analog? Sweet. Okay, so let me introduce the quasisymmetric partials formally. I mentioned shift invariance, and already in the work of Bergeron-Sottile from the 90s, there's this map R sub I that performs a shift and reindexing. Okay, so this map was in the context of Schubert calculus, in fact. So it shoves in a 0 in the ith coordinate and reindexes the remaining as x sub I plus 1, and so on. Okay, so from here, here's the Quasisymmetric divided difference. This map T sub I acting on polynomials going down in degree performs two of these R sub, this shift and reindex operations, takes differences and divides out by what's redundant. So it strikes out the xi from the expression. Okay. So here's an example, and do stop me if something doesn't make sense. My operation is this T sub 1. I'm going to apply it to this polynomial f. R2 will turn this guy, x1 squared x2 to a 0, and will turn x1 squared x3 to x1 squared x2, shift and reindex. And R1 is going to kill both of these things. So you get x1 squared x2 in the numerator, and you're dividing out by x1. So that's the answer. Okay. So one thing I want to take away from this very simple computation is these t's, they act on monomials to produce monomials. Okay, so then they're a little less exciting in this sense from the divided differences. They will produce monomials up to sign. So they can be signs. So there's still some fun cancellation to account for. But when you act on monomials, you get monomials. Okay. Right. Okay, so here's my analog of Schubert polynomials. So there's a bunch of jargon that I'll have to introduce. So let me stick to doing it by pictures, okay? And stop me if something doesn't make sense. My underlying combinatorial data structure is what I will call an indexed forest. And as is the theme in combinatorics, once you have objects, you label them, and you want to track these objects, these labeled analogs. And the way to do it is this very coarse information, you capture it using a generating function. Okay? In this case, it'll be a polynomial. So what's an indexed forest? You start with a copy of the natural numbers. These will be the leaves of the forests that I'm going to plonk on these guys. My forest is going to be a collection of binary trees that sits on top of this copy of the natural numbers. The stuff in orange is the support of the forest. So those are the leaves that this forest sees. Notice that all the support is a disjoint union of intervals. Okay, so there's no gaps between leaves. You must use consecutive sets of leaves. Okay, so this here is an index forest. And what are my compatible labelings? I impose certain inequalities along edges. And I'm going to assign numbers to these black dots, right? So these nodes of the forest, they're going to have numbers, and the numbers must respect these inequalities along the edges. So if you were here for Matthias Beck's talk, you saw p-partitions appear, and this is essentially a p-partition story, except that depending on where your forest is placed, you're imposing a flag condition. Okay. So here's a labeling. Hopefully you can see it. This respects the flag condition. And okay, so this is what you do. You count the number of ones, you count the number of twos, and so on, and you put them together in a monomial. In this case, you get x1 squared, x3 squared, x4, x7, and no surprises next. I'm going to consider the sum of monomials over all such labelings. Okay, so that's the definition of a forest polynomial. All right. Okay, so I want you to observe that the degree of this forest polynomial is the number of nodes. So in this case, you have 6 nodes. So this is degree 6. And if you want to do degree lowering operators, you should have a way to get rid of the nodes. Okay, so the next thing I'll tell you is how to get rid of the nodes so that you drop down in degree. And the operation is this trimming operation. And vaguely, you eat the forest up by starting at the leaves and going towards the root. Okay. So I'll define a trimming operation. So here you have a terminal node. So both its children are leaves coming from the natural numbers. And when I trim, I sort of shrink this to a point. Okay, so this orange picture has become a point, so it gets squished into this new leaf, and that's the trimmed indexed forest. Okay. So you go down in the number of nodes. And what do I want to take from this? This act of trimming a particular terminal node, I'm always going to denote this this f sub 2 by the leftmost leaf here. Okay, so this terminal node, it has a left leaf, and I'm going to identify it with 2. So this division operation is going to be the analog of multiplying by s sub I and going down in length. Okay, so if you're trying to compare the two stories, multiplication by s sub I on the right, trimming a terminal node on this story. And knowing that you can keep doing this W going to WSI map repeatedly, you get reduced words. You should try and do this repeatedly on this forest side as well. Okay. So here's my notion of a descent set. So hand me a forest, any place that I can trim, that's going to be the left terminal set. And then starting from a left term from any forest, I can perform a sequence of these trimming operations and obtain the empty forest. So in this case, there are 2 ways to trim this down to the empty forest. And I can record these sequence of trims in this trimming sequence. Okay. So this is the analog of a reduced word. It's telling you how you can take something of high degree and eat away its nodes until you get an empty set. Okay. I also want you to note, don't want you to, but maybe you should note that this number of trimming sequences is the number of linear extensions. Right? So if you're thinking of this forest as a poset, you're eating stuff from the leaves, going towards the root. So you're sort of doing counting standard labelings of a forest, and that has a hook length formula. And so that number is right there. Okay. All right, so here's the picture again, and I sort of want to give the punchline away. And here's the picture of forest polynomials behaving according to these quasisymmetric divided difference operations. Okay, so for this forest, there are 2 possible t's that I can apply. T sub 2 would give me a 0. And then I get these 2 new forests. Now there's 2 possible t's I can have, 1 each to each forest, and I get this guy down here. Okay, so trimming on the picture side is actually doing this algebraic operation at the level of forest polynomials. And observe that you've got 2 different routes going from the starting forest to this one, which has forest polynomial x1. And this sort of tells you a non-trivial relation between these quasisymmetric divided difference operators. Any questions?
Vasu, based on these pictures, it looks like the trees are always binary trees. Is that correct?
Oh, yes. Sorry, I should have said this. Okay, so Sam's question. I am putting binary trees, complete binary trees throughout the story. The paper actually deals with complete m-ary trees with m larger than 2. But for us, for the purposes of this talk, it's always binary trees.
Thanks.
Yeah, thanks. Okay, so, well, here's the theorem that I sort of want to advocate for why forest polynomials may be considered a good analog for Schubert polynomials. The first statement is sort of by definition, right? So it's contrived. The joint kernel is the set of quasisymmetric polynomials. The analog of the Nil-Coxeter relations are these very simple relations that I've sort of told you right here, T3, T1, and T1, T2, giving the same thing. And turns out that these relations define a well-known monoid that came up in geometric group theory. This is the Thomson monoid. So it's good that this thing already has a name. And it was actually well known, even Wikipedia knows this, that the compositions of these T operations, these monoid, are actually encoded by binary trees, which sort of addresses Sam's question as well, right? So when you compose these T's, you get forests coming up organically. So that's statement 2. And the exact parallel to the Schubert statement, forest polynomials are a unique family which satisfies those 3 conditions. The empty forest gives you 1, the degree is the number of nodes, and these T sub i's act to give zeros or forest polynomials obtained by trimming a forest. Okay, so that's sort of 3 things that we can emulate from the classical story. There's more, but let me just give you a summary so far. Here's the dictionary to go from statements you might know in the setting of Schubert calculus or Schubert polynomials. And here's a translation that you might want to apply and get the corresponding statement in terms of maybe forest polynomials. And let me say that as a sort of an artifact of the theory, Schurs, which are Grassmannian Schuberts, and Grassmannians are things which have 1 descent. If you follow this dictionary, you are looking at things which have exactly 1 singleton left terminal set. And then it turns out that the corresponding forest polynomials are fundamental quasisymmetrics. Okay, so from this theory, it appears that the analog of Schur's is fundamental quasisymmetrics. Okay. All right, so I promised an application. Maybe there's a plural here. I will give only 1 application in the interests of keeping this tight. So the application I'm going to give you is a single slide proof of the non-negativity of the monomial expansion of Schubert's. Okay, and there are already known proofs for this, either using the Lascaux-Schutz-Berger transition formula, which itself relies on Monk's rule, or starting with the Billy-Joker-Stanley expansion and checking that it verifies the characterization of Schubert polynomials that I mentioned earlier. Okay, so you sort of need to know some theorems to arrive at this expansion. And maybe let me give you a bare bones proof which uses sort of zero knowledge. Okay, so XITI is R sub I plus 1 minus Ri. Okay, so that's the definition of the divided difference operation. So you can telescope this relation by summing over all I, and you get that the identity map decomposes as a sum of R sub 1. Remember, R sub 1 shoves in a 0 in the first coordinate and ships the rest, and these operations. Okay, so here's a positive decomposition of the identity map. So here's something I've been hiding from you so far. T sub I is the composite of R sub I and partial I. Okay, so the same partial I that defines Schubert's, you can shove in this R sub I, partial I, for the T sub I, and apply to a Schubert polynomial, and you get something that's completely positive and defines the Schubert polynomial. So everything in sight is easy to do on Schubert polynomials. Xi, Ri are Schubert positive expressions. So you can recurse this and come up with a non-negative expansion for Schubert polynomials. Okay. And you can get to do this equivariantly. There's an equivariant version of R sub I, and you get double Schuberts. It's sort of the same game. And with some work, you can show that this is the pipe dream expansion as well. Okay, so that's a proof of the non-negativity of Schubert polynomials. If you don't like recursions, here's something completely explicit. Take the operator Z on polynomials with 0 constant term. It takes the identity, shoves in a 0 in the first coordinate, shoves in 2 zeros, and does this. Notice that R1 is nilpotent. So this is a finite thing. And then the Schubert polynomial is a sum over reduced words of these ZXR operations. Okay, so you're building a Schubert bottom up rather than top down. Okay, so you start with 1, you do the ZXR, then you do another ZXR until you're done, and then whatever you have, it's going to be a finite expression, and it's going to be a Schubert polynomial. Okay, so here's an example at the very bottom of a very simple Schubert polynomial. Right. So I guess most results on Schubert polynomials in literature rely on this top-down aspect. The only result I know which builds Schubert's bottom-up is this formula of Magyar. And here's a different way to do the same thing. Let me also say that this is not the slide expansion. Okay? So it's indexed by reduced wood, but it's not the slide expansion. Okay, so I sort of had some other results, but in the interests of time and hopefully to get some questions, I will not dwell on them. Let me just stop right here. Thank you so much.
Let's thank Vasu.
Can I ask you a question?
Go for it, Maria.
Okay. So to me, the Schubert polynomials like live inside the covariant ring. And I was wondering if there's a similar place that the Forest polynomials live and like tell you something.
Yeah, so that's the slide I raised. Okay, so thank you, Maria, for this question. So you have the ring of polynomials in n variables. It has Schubert polynomials indexed by Sn, and it has Schubert polynomials indexed by S infinity as long as the descent set is the first n positions, right? We have essentially a same story. You have to replace descents by this left terminal set. So sort of following this dictionary, you replace Sn with indexed forests supported on the first n positions, and you have the same splitting. On the one hand, you get a basis for polynomials modulo positive degree quasisymmetric polynomials, and the other hand, you get a basis for the ideal of positive degree quasisymmetric polynomials. Because the same story.
That's very nice. Thank you.
Sergi?
Yeah, thanks, Vasu. That's very nice. Is there some way to compute these forest polynomials that's not recursive, like summing over something like pipe dreams of whatever?
Yes, so I maybe let me ask, turn the tables and ask you a question. I wouldn't call this P partitions perspective recursive. So here's what I'm saying.
Oh, okay.
You hand me a POSIT, I'm just imposing some flag conditions. You're not allowing all sorts of labels. Where you supported determines the labels you can use. If you keep shifting the forest right, you're allowing yourself more and more labels. But so this would be an explicit monomial expansion.
Yeah. Okay.
Yeah, but there's recursive expansions which exactly look like this guy. So there is a way to define it applying the same trick and acting on forest polynomials and not Schubert's, and you get a similar recursive expansion as well.
Mm-hmm. Thank you.
Hi, Vasu. I had a question about your last formula, the one where you had a sum over reduced words.
Mm-hmm.
So I can't. Are these sub-expressions monomials? Are you summing over monomials, or are those expressions?
No. So if you look at the example below,
Okay.
when I act on one with this, so I think of ZXR as a single unit. Okay, so you shift and reindex, you multiply, and you perform this shoving in zeros and translating operation. So you get polynomial expressions at every stage. And then you do another of these ZXR. So if you look here, you start with 1. The first ZXR does an x1 plus x2. Next ZXR sort of elongates this sum, and you get this elementary symmetric polynomial. So you get big sums at every stage. Yeah.
Okay. So this is very different than the Billy Jakob Stanley sum over reduced words stuff.
Yeah. So that is the slide expansion, right? So this is not the slide expansion, but there is a way to see this expansion at the level of. There's a way to see this expansion at the level of pipe dreams, right? R1 is pipe dreams that do not have any x1s. So those are pipe dreams that do not have crosses in the first row. And then you have to decompose the remaining pipe dreams so that they witness this XI-RI relation. And turns out, yeah, Philippe saw this with balanced tableau first, and then we realized we could translate into pipe dreams.
Okay.
Yeah.
All right. Very cool. Thank you.